This tutorial will show you how to build a plan and execute AI agent in Python using the LangGraph library. A plan and execute agent is an AI system designed to solve complex tasks by first generating a structured plan and then executing each step systematically. It works by first clearly understanding a user's request or goal, breaking that goal into actionable steps, and then following through with executing each of those steps. Throughout execution, the agent dynamically adapts, meaning it can handle unexpected situations, revise its plan if something doesn't go as intended, and make adjustments to reach the goal efficiently. Use cases for plan and execute agents include customer support automation, job candidate shortlisting, event scheduling, and personalized recommendations. For our purposes, we'll build an agent that recommends live music events tailored to user preferences. It will dynamically adjust its recommendations based on real-time information. Let's go over the workflow, but first, let's quickly understand how AI agents work with LangGraph. The boxes you see represent nodes, each serving a specific task or step in our agent's process. The lines connecting these boxes are called edges, and they illustrate the flow of information and decisions from one node to the next. Conditional edges, represented by dotted or dashed arrows, indicate paths taken only when specific conditions are met. The goal of this tutorial is simple. The user describes their musical preferences, and our AI agent creates a tailored plan to find 3 live music events that match these interests. This diagram visually represents how the agent systematically moves from planning and recommending events to verifying event details, and finally, delivering a concise and informative set of recommendations. First, starting with the planner node, the agent interprets the user's preferences and forms an actionable plan designed specifically around the user's musical tastes. Next, the Recommend Music Event node takes this plan and identifies 3 potential live music events. The Event Lookup node then verifies each recommended event by gathering key details such as venue location, time, and ticket availability. If any event lacks sufficient details, the agent loops back to the Recommend Music Event node and then excludes problematic events. Finally, the executor node compiles the verified information into concise, ready-to-use final suggestions for the user. In addition to using LangGraph as our agentic framework, we'll leverage Perplexity Sonar as our AI model API. We'll be using the standard Sonar Perplexity model, which is built on top of Meta's Llama 3.3 70 billion parameter model. The added boost of Sonar is that it provides real-time internet web search access, which eliminates the need for the AI agent to perform separate tool calls. To do this tutorial, you'll need to get an API key for Sonar by going to sonar.perplexity.ai and then clicking Start Building. This will bring you to a quick start guide, which will describe the steps for setting up an API key. Follow these instructions and load just a few dollars of credits onto your account. The cost of the Sonar model is extremely low, at $1 per 1 million input and output tokens, and $5 per 1,000 searches, which is half a penny per search. Once you pay, you can refresh the page and generate an API key. We can now prepare our Python environment. In your terminal or command prompt, create a new virtual or Conda environment with Python version 3.10. Then use pip to install LangGraph, LangChain, LangChain Community, LangChain Core, OpenAI, typing extensions, and IPy kernel. Next, move over to a code editor that supports Jupyter notebooks and import the libraries and the necessary modules. From the typing and typing extensions libraries, we'll import tools to create clearly structured state definitions for our agent. From LangGraph, we'll import core components like StateGraph, as well as start and end, to build and manage our workflow. We'll also bring in add messages to manage message handling within our agent. We'll use Chat Perplexity to interact with the Perplexity Sonar API. We'll also import message classes like human message and AI message, which help us structure interactions between the user and the AI agent. Additionally, we'll import utility modules like OS to handle environment variables securely, datetime to manage date-related tasks, and IPython display to visualize the workflow diagram. We'll start by setting our Perplexity API key as an environment variable, then passing that key into the chat perplexity function. Here, we'll also specify our AI model, Sonar, and set the temperature to 0.5. This temperature value balances deterministic output, which would be a 0, and more creative or stochastic output, which would be a 1. You can test different values of this parameter and see what it outputs. Next, we'll define our agent state using a typed dictionary. The agent state is how the agent remembers and manages information throughout the workflow. In our case, the state clearly specifies the types of information the agent will track, including messages exchanged between the user and the agent, the music event recommendations it generates, detailed information about each event, which node or step to execute next, and a running list of events that should be excluded from future suggestions to ensure fresh recommendations. At this point, we can create functions for each node in our workflow. The first is called Music Planner. This node reads the user's music preferences and generates a simple plan. It builds a prompt using today's date and sets the AI as a live music expert. In this case, I've set it to Brooklyn, New York, but you can change the location or even update the code so that the location is set by the initial user prompt. The AI then outlines a plan to find 3 music events for the night. Once the plan is ready, the node updates the agent's state and moves to the next step. We next define the music recommendation node, which suggests 3 live music events in the first iteration. In later iterations, it also excludes events that lacked enough information. This function retrieves the user's preferences and the previously generated plan from the state dictionary, accessing them from their respective keys. Using this, it constructs a prompt asking the AI to recommend 3 different live events happening tonight in Brooklyn. It ensures none of the recommendations come from the exclusion list. The AI returns a simple numbered list of event names. The node then updates the state dictionary with these recommendations and moves to the next step. We now define the event lookup node, which is responsible for gathering details about the recommended events and updating the exclusion list when necessary. It retrieves the current recommendations from the state dictionary and initializes an empty list to store event details. The function then constructs a prompt for each event, asking the AI to find key information such as venue, time, address, and ticket availability. Once the AI returns a response, the function checks whether the event details are complete. If critical information like the venue, time, or address is missing, the event is added to the exclusion list, ensuring it won't be recommended again in the next iteration. If an event is sold out, that fact is noted, but it is not excluded unless other details are insufficient. After processing all events, the function determines the next step. If at least one event lacks sufficient information, the workflow loops back to the recommendation node to generate new suggestions. Otherwise, it proceeds to the executor node to finalize and present the results. Finally, the executor node compiles the final output summary. It retrieves the list of recommended events and their details from the state dictionary. Using this information, it formats a structured response listing the 3 live music events for tonight, including any available venue, time, and ticket information. If details are missing for any event, it indicates that explicitly. The formatted output is then stored as an AI message and returned in the updated state. So at this point, the agent has completed its workflow, delivering live music event recommendations for the user. To bring everything together, let's take a high-level look at how our agent works and why we use a structured workflow. LangGraph provides a stateful execution framework, which allows us to define and connect different nodes into a structured graph. This is why we create a workflow diagram, because it visually represents how data flows between nodes and helps manage decision-making within the agent. Instead of writing a single long function that handles everything at once, we break the problem into clear steps. This next section is where we create the graph that defines our agent's workflow. We start by initializing a state graph using our structured agent state. Then, we add the node functions that we previously created. After defining the nodes, we establish graph edges that define how the workflow progresses. The planner node leads into the recommendation node, which then moves into the event lookup node. The event lookup node is unique because it has a conditional edge. If any event lacks enough details, the decide event lookup next node function determines whether the workflow should loop back to the recommendation node for new suggestions or move forward to the executor node to finalize the results. Once these connections are defined, we compile the full graph. Okay, so we're ready to run the agent. We start by giving it a simple initial input. Here I've put, I'm looking for some cool jazz music tonight in Brooklyn. We package this into our state dictionary and initialize the other fields, such as recommendations, and excluded events as empty. Then, we invoke the inputs into the compiled graph in order to process our request. We'll run this and see how everything works out. If you noticed earlier, I added lots of status updates in brackets at every step of the code. If we start from the top, we see movement from the planner node, to the music recommendation node, to the event lookup node, to the decision node, to the executor node. In this case, there was no reason for the agent to cycle back from the event lookup node to the music recommendation node, because there was ample info on the three chosen events. If we look at the agent output, we can see that the first returned event is New Orleans Jazz, with Constantine and the Constellation playing at St. Maisie Bar and Supper Club. They're definitely a jazz band, and I confirmed on the venue's website that the show is in fact set for tonight. The second event returned is Kaiju Big Battle, which is definitely not a jazz show. Look it up on YouTube. But it is an event that is actually happening tonight. The final event at Union Pool is also confirmed to be tonight. It is not jazz, but the agent accurately makes a note of that. Let's try running this again. This time around, the second result is definitely jazz. The third remains the Union Pool event, which is not jazz, but similar to the first run, the agent at least mentions that it is not strictly jazz. On most of my tests of this code, at least two of the results were jazz related, and almost all events were events happening tonight, as of when I recorded this. So there's definitely room for improvement with the Perplexity Sonar Web Search AI model. To be clear, the Sonar model is their base model, so performance would likely improve if I had used Sonar Pro or one of their web-connected DeepSeek R1 models. But overall, we can see just how powerful AI agents can be when using a plan and execute workflow. If you found this video useful, make sure to like, comment, and subscribe to the Deep Charts channel for more tutorials on the latest AI models and tools.